So integrating factor, what is it? Why do we need it? Well, we need it, this technique, to solve differential equations of this type. dy dx plus some function of x, p of x, times y is equal to g of x, some other function of x. Okay, so when we have a differential equation of this type, we need to use the integrating factor technique to solve it. So let's class this ODE. It is a first order because it only has a first order derivative of y, no second or third order. It's linear because it only has y to the power of 1 and dy dx to the power of 1. A non-linear ODE would have dy dx squared or square root y, etc. Okay, so this is linear, and it's non-homogeneous. Okay, so non-homogeneous, which means the right hand side is not equal to 0. However, this function g of x could equal 0 and be a homogeneous ODE, and then we could still use the integrating factor technique to solve that. Alright, so what is the integrating factor technique? Well, with creative foresight, we might say, let's multiply everything in this function by u. So I'll have u times dy dx. Well, u is a function of x. Let's introduce some function of x called u and multiply it by everything here. So I've got u times dy dx plus u of x, p of x of y, equal to u of x, g of x. Okay, so what I do to the left hand side, I've done to the right hand side, which is allowed. Okay, what's the next step? Well, I've got the derivative times some function plus the function times the derivative. So if I use the chain rule, so remember the chain rule, so the derivative of a function f and I'll call it h, so the derivative of a function f of x times h of x is equal to f dash of x, h of x, plus we keep f constant and take the derivative of h. Okay, that's the chain rule. Or, sorry, not the chain rule, the product rule. Okay, that's the product rule of differentiation. That's something we learned quite early on. So let's look at this equation. If I call this, well, f is the derivative, so I'll call this f. H of x I'll call u, so that's f, that's h. And over here, f would be my y, because that's the derivative, so f dash of x, f of x, and u of x will be equal to u of x p of x. So that whole thing will be equal to h dash. Okay, so therefore my h is equal to u of x, my h dash is equal to u of x times p of x, and my f is equal to y, and my f dash is equal to dy dx. That seems fair. So therefore, I can write the right hand side like this. I can, well, if that's what it's equal to, then I can write it like this. So it's equal to d dx times f of x, which is y, times h of x, which is u of x. So, and that's going to be equal to u of x, g of x. That's pretty convenient because now I can solve in terms of y. I can take the integral of both sides. So I've got y u of x is equal to the integral of u of x, g of x dx. And I can solve that and then just divide by u of x. So the question is, what is u of x? So what function u do we multiply every term by so that we can write it in this form? Okay, which is easily solvable. Well, we need to choose u such that its derivative is equal to, well, h is equal to u, so the derivative has to be equal to itself times some other function, p of x. So let's solve this. Well, this itself is a differential equation in terms of u, but it's separable. So du on u of x is equal to p of x dx. Now we can integrate both sides of this separable ODE. du on u of x is log e u of x, and that's equal to the integral of p of x dx, which I can't simplify. And over here, if I take exponential of both sides, I get u of x is equal to e to the integral of p of x dx. Okay, so the function we choose to multiply every term by in our differential equation is the u is the function u is equal to e to the integral of p of x dx. Okay, so we find the integrating factor u by looking at the coefficient of y, p of x. Okay, two things we've got to make sure of is that this is a plus, so if it was a minus, that would go into the function p of x, and the coefficient of dy dx is 1. Okay, so that is where the integrating factor technique comes from. It's by seeing that if we introduce a function, we can use the product rule to help simplify, and our choice of u of x, such that we can do this, is equal to e to the power of the integral of p of x dx, where p of x is the coefficient of y, a function of x, which is the coefficient of y, with a +1 out the front.